course, I'm going to have a lot of differences between an ideal filter and a filter that I can actually implement, a real filter. I'm going to start with first order filters, as they're the simplest filters to consider, and they're going to behave the same exact way that any first order system is going to behave. And so we already have a sense as to what it will look like on our kind of magnitude ratio plot. But let's start on that magnitude ratio plot, sketching an ideal, and I'm going to, in this case, use a low pass filter as an example. I could do a high pass filter as well. I'm going to plot the ideal case for that low pass filter. Right? I have a magnitude of 1, and then I'm going to transition to a magnitude of 0 at some corner frequency right here. And that is an infinitely sharp transition. That's a vertical line, right? Everything gets through perfectly in my pass band here. Nothing gets through my stop band. So in contrast, for my first order system, in this case I'm going to sketch this in dB, so this doesn't translate perfectly, but I hope you'll forgive me for that a little bit. So I have a minus 3 dB point right here, and then I'm also going to go down my 20 dB levels that I saw for my first order system, and I'm going to mark my corner frequency once again and a couple decades above that corner frequency, so 10 omega C and 100 omega C. And I'm just going to plot the general magnitude response of a first order system, and that's going to be equivalent to my first order filter response. So I'm at minus 40 dB at 100 omega C, I'm at minus 20 dB at 10 omega C, I'm at minus 3 dB at omega C, and I'm pretty close to 0 dB when I'm a decade below that, right? So I'm going to go through here and then roll off at my standard minus 20 dB per decade. So below my corner frequency, my real filter, so this yellow line here, remember, is my first order filter response. It looks fairly similar in this passband area right here. Now where things look very different is in the stop band for the ideal filter. Stop band in the ideal filter was everything from omega C on up, right? But it's a little different in the real filter. So at 10 times higher than that corner frequency, whereas I get no frequency content through in my ideal filter, I still get 10% of the magnitude of whatever was at this particular frequency through my filter, right? And 10% is not nothing. So 10% can be pretty high. So oftentimes what we define, at least kind of 2 orders of magnitude above this corner frequency as, is a transition period, and then everything above that, so now I'm only at 1% of whatever signal is getting through at minus 40 dB, and that, everything above that, would be my stop band. And you'll see these definitions vary a little bit. Some people will call everything above omega C the stop band, but I think it's a little more appropriate to call it a transition band in this case. So hopefully one of the things that you see from this plot, though, is that a first order filter, whereas it's easy to implement, is nowhere close to the kind of ideal filter that you might want. And that's primarily defined by the lack of a really sharp cutoff between the pass band and the stop band. In this case, I'm saying that I have 2 orders of magnitude of frequency where this thing is transitioning and I'm still getting reasonable amount of frequency content through. It's not perfect transmission, but it's attenuated in some fashion. The easiest way to implement a first order passive filter, and passive meaning there's no op amps or any kind of other active elements in my filter, is through the RC circuit that you should be pretty familiar with by now. So I have a single resistor, single capacitor, I have some input voltage coming in here, and I'm measuring my output voltage across the capacitor. So this is a low pass first order filter as well. So I could go through and do the math and show that this is a first order system, but hopefully you believe me on that by now. And I'm going to have a time constant for this particular circuit of RC. So that is in units of seconds. And I know also for my first order system frequency response, I'm going to get a magnitude ratio of 1 over the square root of 1 plus tau omega squared. So to write this instead in terms of the corner frequency that I'm using in my filter definitions, I'm going to define omega c as 1 over tau. In this case, it's going to be 1 over RC. So I'm going to rewrite this magnitude ratio as 1 over the square root of 1 plus omega over omega c squared. So to remember what this means in terms of my dynamic signal that I have at my input, what this is telling me is that my V out over time, at least in the steady state, is going to be that magnitude ratio. Remember, if VI is some A sine of omega t, so I'm going to get at the output magnitude ratio times A times sine of omega t plus some phi times omega as well, right? I'll still have that phase shift. My filters can introduce a phase shift similar to the general first order system. So if I'm at a frequency where omega is much smaller than my corner frequency, this term is tiny. I'm just going to get a magnitude ratio of 1, and I'm going to get my input signal through to my output, right? It's going to look effectively the same. If I'm at a much higher frequency, if omega is much larger than omega c, right, then I'm in that transition or stop band where m of omega is going to be smaller, so say 0.1, 0.01 times the original amplitude of the system. So that does not get through as easily as the lower frequency content, which would make sense. I'm trying to make a low pass filter here. I can implement these first order passive RC filters in either a low pass or high pass configuration. And a low pass is going to look fairly similar to what we just drew, not surprisingly. So I'm going to be at a magnitude ratio of 1 or 0 dB below the corner frequency. At the corner frequency, I'll be at minus 3 dB. And then I'm going to get a roll-off of minus 20 dB per decade after that corner frequency. High pass filter will have that magnitude of 0 dB far above omega c, right? I'll be at minus 3 dB at omega c, and I'll be rolling off, or rolling up perhaps in this case, at, this would be plus 20 dB per decade slope right there. So this now is defining my transition and stop band, and my pass band is at the higher frequencies. So this, of course, is my high pass filter, and this over here is my low pass. So the circuit that I'd use to do that low pass filter, I already sketched for you, but in this case, I always think of it as effectively an impedance divider. For a low pass filter, the capacitor is going to show up in the lower portion of that impedance divider. So in this case, I have a VI input and a VO output. For the high pass filter, it's going to be opposite. So the capacitor is going to show up in the upper portion of that impedance divider, and the resistor is in the lower portion. So here I have my input and my output, and I'm going to define these as R and C. I already gave you the magnitude ratio of this, but I'm going to write it one more time. So in this case, I'm looking at 1 over the square root of 1 plus omega over omega c squared, where omega c is the corner frequency, and omega c is 1 over my time constant RC. For the high pass filter case, it's going to look somewhat similar. In this case, I'm going to have my omega over omega c in the numerator as well, and square root of 1 plus omega over omega c squared in the denominator. So in this case, if I'm at a very high frequency, so this term is dominant in comparison to 1, so I effectively have an omega over omega c in the denominator, then I'm going to get a magnitude ratio of 1, as I would expect at these high frequencies. If I'm at a lower frequency, that's where things get interesting, and I'm basically going as omega over omega c. All right, so I can either make a low-pass filter or I can make a high-pass filter. That's first order, so it's not a very good filter, but it's sufficient for a lot of applications. And I can do that with a simple resistor and a capacitor. And I can give you the magnitude ratio as to how that will roll off depending on the R and C that I have here. Right? Actually, I should point out this high-pass filter, omega c is defined in exactly the same way, right? Just 1 over tau, or 1 over RC. Let's do a quick example where we're going to design a filter based on some of the noise types that we've talked about as well. So in this case, I have a resistive sensor. It has a nominal resistance of a mega ohm, and I want to enable a minimum detectable signal of a millivolt while maximizing the low frequency bandwidth that I have available. And in this case, I'm assuming that Nyquist-Johnson noise is the dominant noise source. And remember that for Nyquist-Johnson noise, I have an RMS voltage squared associated with that resistive sensor. That's going to be 4 kBT times R times delta F. Right, where delta F is my bandwidth of interest in this particular problem. So bandwidth right here, that's the same bandwidth that I'm looking at right here. Right, the other part of this problem to consider is this minimum detectable signal of a millivolt. So if I want my minimum detectable signal to be 1 millivolt, and I assume that I want an SNR of 3, then I need my noise, in this case, to be approximately 333 millivolts. So I'm just going to write 0.33 millivolts, sorry, 330 microvolts, or 0.33 millivolts. And another useful number to keep in the back of your mind is that kBT at room temperature, so around 300 K, is going to be equal to 4 times 10 to the minus 21 joules. So now I have everything I need for calculating what this bandwidth is going to be. I have the noise that I'm trying to reach here, I have my kBT, I have my resistance for my resistive sensor, and so I can calculate then my bandwidth. So let me rewrite that equation in terms of bandwidth. So now I have delta F is going to be equal to that RMS noise squared divided by 4 kBT R. So in this case, this is going to be 0.33 millivolt squared divided by 4 times 10 to the minus 21 joules times 10 to the 6 ohms. This is going to be approximately equal to 6.6 megahertz. Right, so what this has given me, my corner frequency. Right here, it's FC because I've calculated this in terms of hertz. So I've got a corner frequency now for my filter, and I'm trying to design a low-pass filter. So in this case, I want my filter to look like an RC circuit, where my capacitor is down here, my resistor's up there, so there's my R, there's my C, my input voltage, my output voltage defined here. So here's my RC filter. And now that I know my bandwidth that I have here, I need to pick some parameters for R and C. Obviously, I have an under-constrained system, so I'm just going to pick an R. So I'm going to say, let's set R equal to a kilo ohm, and let's calculate then what C needs to be equal to. So I know by definition that omega C is 1 over RC. So that equivalently, FC is 1 over 2 pi RC. So I can back out then C is going to be equal to 1 over 2 pi times R times that corner frequency. So if I plug in the kilo ohm that I chose for my resistance here, and I just randomly picked that. I could have picked 10 kilo ohms or 100 kilo ohms. If I picked a kilo ohm, Here I plug in the 6.6 megahertz. That is my corner frequency. That's my delta F that I can get out of this. And I'm going to get a capacitance of approximately 24 picofarads. Right, so this is my filter design now. I have this topology. Right, so my filter is a low-pass filter. I've chosen this value for my resistance, and I've calculated this value for the capacitance. That will give me a corner frequency of around 6.6 megahertz, right? And ultimately that will mean that I will get a noise level in my system of about 0.33 millivolts, which means that I can have a minimum detectable signal of a millivolt.